Okay, one of the concepts we'll learn in this chemistry class are atomic models. How do you represent an atom that's too small to see? Do we just draw a ball? Do we draw, dots and circles? And how do we actually represent the atom? Well, you see, it all started with J.J. Thomson's discovery of the electron. You see, he had this Crookes tube, it's called, and in a complete vacuum, he hooked up an electrode on one side and a positive on the other side, and there was a beam or a ray that was going through this material that would hit a phosphor screen. And it could be deflected by both a magnet or an electric field, okay? Now, the cathode rays themselves are composed of electrons, and he found that the electron was thousands of times lighter than a hydrogen atom, so they discovered the first subatomic particle. Now, what you need to realize is that electrons are negatively charged, and negative charges repel one another. This is key to understanding the models of the atom, okay? So a negative electron and a negative electron will repel each other. And if you have two positive charges, they will repel each other. But if you have a negative charge and a positive charge, those are attracted to each other, much like, the Earth and the Moon are attracted to each other, or a rock, if you drop it, it's attracted to the Earth, okay? Now, J.J. Thomson, who discovered the electron, came up and proposed the Plumb and pudding model. You could think of this as a blueberry muffin or a chocolate chip cookie, for example. And so since he discovered the electrons, he thought that they might be central in the atom, okay? So he proposed that electrons are centrally located in the atom, dispersed and spread out a little bit. But the idea then is, well, what holds these negative charges into the atom is the dough, right? The dough holds the chocolate chip cookies in the chocolate chip cookie, right? And so he proposed that the positive stuff holds the negatively charged electrons into the atom, all right? And that was rejected sometime after when Rutherford came along. But that was the first attempt to try to draw maybe what the atom looks like on the inside. Now, Rutherford is famous for his gold foil experiment. This is explained in greater detail in the other slides that I've prepared. But basically, this slide here outlines the experiment, not the model of the atom, but the experiment, okay? So he had a piece of lead that was drilled out, and inside of that was placed radium. Now, radium is a radioactive element, and it basically ejects alpha particles, which are helium nuclei, at 80% the speed of light. Now, most of these pass through the gold foil untouched and reach the back of the screen and can be detected. Just a few are deflected at a small angle, and then very, very rarely is an alpha particle backscattered. Okay, so that's the experiment. That's explained in another video of mine in much greater detail, as well as the OpenStax textbook. Now, this is his model. He found basically a few different things, okay? First, the atom is very small, compact, and positively charged, all right? The atom is mostly empty space, all right? And then the electrons are very small and far away from the center. The textbook has some great analogies of this. If you're in a very large baseball stadium, the nucleus of the atom is going to be the size of a blueberry on home plate, and the stadium just represents mostly empty space. And there might be a few people, janitors or something running around the stands picking up garbage or something. Those represent the electrons that are just out floating around somewhere, okay? Now, the center of the atom is mostly made up of protons, which we give symbol P. So this is the second subatomic particle here that we're talking about. Now, protons are positively charged, all right? Now, there's a problem with this model because protons are positively charged and other protons are positively charged. How can these be very compact and tightly held together and in close proximity into the nucleus? Don't positive charges repel other positive charges? Yes. So the nucleus would explode due to Coulombic repulsion of positive and positive charges. So it wasn't until 1932 that the neutron was discovered by James Chadwick, who's considered to be the father of nuclear chemistry. Now, the idea here is that neutrons are the nuclear glue that holds protons together in the nucleus through the nuclear strong force. So I just like to think of neutrons as nuclear glue, okay? You know how like you have Thanksgiving dinner and you have two of your cousins that are just always fighting, so your aunt and uncle sits right in the middle to kind of bring everybody together and keep the family close. So that's what a neutron does, okay? Two protons are going to be repelling one another, but the neutron is going to kind of sit in the middle and kind of hold the two protons together through an even stronger force called the nuclear strong force. All right, so you might be interested and wondering, now what are these nucleons in the nucleus? Now, a nucleon is a proton or a neutron. Now, protons and neutrons themselves are made of smaller particles called quarks. Now, quarks are held together by the nuclear strong force as well. Now, we won't cover quarks in chemistry, but just be aware that there are smaller particles and there's much more interaction and complexity there, okay? But in chemistry class, we're not going to be doing very many nuclear reactions. A proton's always going to stay a proton, a neutron's always going to stay a neutron, and we just count them and we add their masses and, you know, things like that, okay? Now along came Bohr. Now Bohr was concerned with the electron. How are the electrons moving in an atom? Are they in different orbits like the planets are in orbits around the sun, or are they all jumbled up in one location of the atom? So Bohr's quest to understand the electrons came up with the Bohr model of the atom. There's some stamps here commemorating him, and he won the Nobel Prize in 1922. And what he found was that electrons are only in certain orbits. So here's the Bohr model of carbon. Carbon is element 6, so it has 6 protons, and I guess this particular one has 6 neutrons as well in the nucleus. So that light green circle is just highlighting maybe where the nucleus of the atom is, okay, where all the protons and neutrons are. And this is not to scale. Now, electrons are thousands of feet away from that, right? If it were to scale, the electrons are very far away from the nucleus, and the electrons here are in certain orbits. Okay, so you can see a ring. There are 2 electrons in there, and then there's a second ring. You can see there's 4 electrons in that outermost ring. So we'll look at this later on in greater detail in the class this semester. And finally, we have the quantum model of the atom. We will look at this later on in this semester as well. And Schrödinger is the father of quantum mechanics or quantum chemistry. And so he came up with the model of the atom of where the electrons are. And he did a completely mathematical analysis of the electrons in an atom. And what he found was that electrons are like waves. They're not at a particular location. They're kind of spread out. Okay, so here's some water droplets hitting a surface of a pond or something. And you can see how, yes, water is a single drop that's hitting that, but what results from that is a wave that extends over the whole pond. So what he found was that electrons could be treated as waves. That means they're everywhere. And we represent atoms as electron clouds. So that's just a tidbit view of what different models of the atoms we have. Looking forwards to this semester in chemistry. Thanks for watching. Please like, please subscribe. Have a great day, everybody.